My name is Jose Rico, CEO and founder of this company called Northern Waves, and we are specialized in additive manufacturing for communication devices or microwave components. And as it is always better to touch it and see it, I brought some components that I will pass by that you can realize. I will put those three, and then you can start passing them. All those components are made in aluminum alloy, and they are quite lightweight, as you can feel it. All of them are for aerospace applications. Regarding the talk, I will introduce a little bit the company. This is a startup company based here in Sweden, Northern Waves. Then I will cover how components or communication devices systems are done now with three main techniques: subtractive, casting, and then the new technology, additive manufacturing. Then I will talk a little bit on how we can combine simulation and innovation. Because even though we are a hardware company, we are building and manufacturing things, we cannot live without the simulations. We need to do everything before in the computer. And then I will just conclude with some products and examples. I would like to start by introducing a little bit of history of communication devices. So if you remember the first generation of mobile communications, we started making calls between us. In the second generations, we jump into SMSs, we can send messages. Third and fourth generation, we jump into internet. We can have apps, we can send mails, we can send images. And then we are now getting into 5G, 6G, where everything is going to be interconnected. And all those devices or systems are be connected through the air with antennas. So that's why I started the company Northern Waves, to try to have and to push the limits of this system and to try to realize whatever you have in mind, because you are not limited anymore to the design or to the traditional manufacturing techniques. You can have new shapes, you can have new possibilities that come out of your mind that were not even possible before. And many of our clients, as we used to hear, we're working with aerospace companies, also defense, like Viasat, Ericsson here, Saab, Fraunhofer in Germany, and also with a lot of universities that are pushing and actually innovating in the European framework. The products that we're offering now, it's a combination of different metallic components. So we're covering geodesic lenses for 5, 6G networks. We're also doing horn arrays and geodesic horns, mainly for aerospace and then different sectors. We are doing a lot of ad-hoc components. Since we are doing additive manufacturing, we can be quite adaptive to our clients' needs. And we're also doing a lot of waveguide for testing facilities. What we are offering as a company is, apart from whatever you have in mind, try to build it. We are adapting components that you already have in your product line from traditional techniques to additive manufacturing. We are using cutting-edge technology to create and to craft these designs. We are also designing from scratch. So if someone asks us, okay, we need to have this component for this specific application, we are designing and covering from the simulation of the electromagnetic mechanical design. We are also building and testing. So we offer the whole process. Now, I would like to jump on how the components are done now. There are three main techniques, which is subtractive, which is the typical CNC milling. You were having a big block of metal, and you will start cutting the material. This is well spread. You have a lot of different materials. It's well established in a lot of different sectors, but it's a lot of material waste because in the end, you have a big block of metal and you start cutting and making a lot of waste. It is limited in terms of design complexity, and this is the worst part of this technology. You are putting constraints to the designers, so you are not innovating enough. And the other thing is, it's not leading with the demand of the exponential growth in LEO constellations, 5 and 6G networks. So you need to have some technology that is adapting to this huge and evolving and exponential increases in the technology. I have some examples here of a geodesic antenna developed by the European Space Agency and a system developed by Pasquale System. And if you take into, if you see this image, at least from my side, it seems quite bulky. It has a lot of pieces. You have many screws. So it's really complex. We will need to solve this. And if you think how much is a kilo to send it to space, is around 50k euros. If we can reduce 3-4 kilos in that system, you can reduce a lot of the cost of the overall sending to space. Next technique is called casting. It is well spread. Basically, you have some mold where you put some melted material inside, and it solidifies to create the desired structure. It is also widely spread. You have a lot of different materials. You can use plastic or you can use metal. But the problem in this technology is the initial cost of the tools are really, really high. So if you're not going to make millions of units, it's not really your choice. And the second thing is quite limited also in design. So you are putting a lot of the design constraints. So you're not able to innovate a lot. Another thing is the lead times typically for this technology are quite high, so you're not dealing with the demand. Some examples of components done by casting are these horn antennas. And finally, the technology that we're expert on is called additive manufacturing. And in this case, you don't have anything on your building plate, on the platform that you're building. You start adding by layer deposition of different materials, the electric or metallic, and then in some way you are solidifying or bonding these structures together. It is way faster than their technologies. It's also cost effective. It is accurate. As you can see in some prototypes, you can achieve things really tiny, like 100 microns minimum feature. And the best thing is that you can adapt to shape forms. So in this case, this antenna is completely lightweight because you are adapting to the cavity that is inside. I will focus on this example later. There are three main trends in the technology of additive manufacturing for these communication devices. You can use it for grading lenses with metamaterials, like this one on the top. The problem is once you go into higher frequencies, such as the industry is going now, you're having losses, and this is not demanding with the performance that you need to have on the system. You can also have the electric things that you, after that, coat it, or you can apply some kind of metallic solution to make it conductive. But again, if you go into higher frequencies, or if you want to send it into space, you're having outgassing, so you're not dealing with environmental constraints. So our expertise is on metallic-only solutions because we enhance the performance of the mechanical structure, and we're also avoiding all kind of dielectric losses associated with the technologies. This is the most common 3D printing technique that you may know, maybe some of you have at home, which is the FDM, where you have the filament spool, and then you're coming through a nozzle and you're creating the part on the building plate. You can create cool things like this dielectric lens. But as I was saying before, this has a lot of disadvantages, like having dielectric losses. So we are focusing on the technology called laser powder bed fusion, LPBF. This is the machine that we're using, where in the dispenser you have metallic powder. It can be aluminum alloy, can be stainless steel, titanium, or other materials. This recoater tool is creating a uniform layer of around 30-50 microns, more or less, on the printing bed. And then a laser is an energy source that is solidifying and creating different bonding the particles in the building plate to create one solidified layer. Then the building plate is coming down, so you're creating another layer, and you're making the part by adding a layer by layer deposition until you finalize have your part. This is the same part I was passing before now. And just to give you an overview, this is the real-time process. So here we have in the gray, this is the metallic powder, and the shiny part is solidified by the laser. This is real-time. Now, explain the technology, I would like to give some examples of how we are combining the simulation with our innovation with these AM processes. And here, well, I might need to talk later with Andreas about Motzin because this is the process now, and as he was mentioning, maybe it's quite complex. The upper side is completely digital, and the other one is regarding the hardware. So we're starting with electromagnetic simulation, jumping into the 3D model or electromagnetic vacuum model. We are then jumping into the mechanical one, and then after that, when we have the finalized model, we just jump into the manufacturing, assembly, and finally testing. So the first step is to start from the theory and to start from the equations, which is not really funny, but that's how it is. So we start designing in CST, Microwave Studio, where we can do full-wave simulation, or we can do 3D, 2D, depending on the structure. We analyze the electromagnetic behavior of the different structures. And as you can see in that image, you can see the electromagnetic waves propagating. And this is an example of the software. So in this case, this is an elliptical Lunipool lens. You're having different ports, and each of the different ports is creating a beam in a different direction. So you can scan and point your client or your target in the different areas. This is something that we are developing now for Ericsson for the future fan-flash communication sector. Once you develop that model, and unfortunately now CST is not really available to create a really complex structure, we jump into SolidWorks to create the actual CAD design, because it's easy for us to design this vacuum or electromagnetic model. As well as I was explaining before, we can create 2 or the 3D structures. Once we have this electromagnetic of vacuum model, this is the cavity that is going to be later on inside the metallic box, we create the mechanical model. And as you can see in the image, this seems quite lightweight because it's conformal to the shape I was mentioning before of the cavity. In this case, we're again performing this in SolidWorks from the salt. We're creating the whole assembly with the different connectors and everything. And once the mechanical model is finished, we jump into CST to validate the last full weight simulation with the whole model. Once this is done, we jump into the actual real world, so we actually manufacture the things with the LPBF. If we want to do metallic components, as I was saying before, we're using this LPBF technique, and if we're using some dielectric components, as other companies are doing, we are using this FDM or SLA. Once the manufacturing is done with all the supports and everything, as I was saying before, we need to do the assembly. We typically do some post-processing to reduce the roughness, to improve the quality of the surfaces, or maybe to do some assembly. So in this case, we were putting all the connectors with the threading and also doing some blasting to reduce the roughness. And finally, after that, what you need to do is you need to do the experimental validation, because, I mean, it can be pretty funny, it can be pretty beautiful, the prototype, but you need to test it. And if it's not working, you need to build something else. So we measure the scattering parameters, that is how much energy is propagating, how much energy is coming back from the system. You also do the radiation pattern, so this is how the antenna is radiating, which is the shape that is creating this antenna. And we typically do that in an echo chamber, which is that thing with the cones that you can see in the image. And finally, which is really important, you validate with simulations to check that everything is performing nice. So in this case, this is the antennas I was explaining before. And here we had in solid lines the simulation, and in dashed lines the measurements. That each of the different ports was creating a different beam, as I was mentioning before. And here is the 3D pattern, so how if each different beam is creating a different way. And now I would like to explain some examples of how we develop this innovation with additive manufacturing for some clients. And we started first with the European Space Agency to develop a half-lunar lens, which is a compact antenna or system that, as I was explaining before, it can create a different beam in a different direction, so they can use it for scanning. This is the idea of the model. So each of the different ports, and we can see it here from the system simulation, each of the different ports create a different way so that you can scan from 0 degrees to plus 60 degrees. So this is pretty nice for them to follow LEO satellites in the constellations. And this is the 3D model of the cavity or vacuum model. But they had a problem because they started this project before without working with us. They were doing this prototype in milling, so they were putting two parts created by this subtractive technique with a top and bottom plate that later on they assemble with a lot of screws. And as you can see in this image, they were having some misalignment errors making the assembly. This misalignment, it can create a degradation in the performance, and it can also create leakage. So all these things are reducing the performance. So basically the problems that they were having was misalignment, leakage, and high cyber levels. This means that the radiation pattern was pointing different orientations, not desired. So what we did is we started from the same vacuum model, so we didn't want to change anything. And the idea was, okay, if they were doing two parts, the first thing is we need to combine them both and take out all the screws. Then we create a monolithic version. Instead of having two pieces with misalignment and leakage, we only have one. After testing this, we created a compact and lightweight model, because as I was explaining before, for ESA or any people sending something to space, a kilo is 50 euros, so 50k euros. So if we can reduce mass, it's a huge improvement for them. And in this case, we reduced the weight 74%. Here are the prototypes that we built. The first one was the single block, let's call it, 800 grams. But the compact and lightweight was only 223 grams. We reduced 1.2 kilos from the previous prototype, so they were really happy. And hopefully we can test this soon in space. And not only that, but we improved the performance, because as I was saying before, we were having silo levels. So these parts here were from the milling prototype. We reduced them a lot, almost 10 times. So we improved the performance while reducing the weight and also reducing the complexity of the whole system. They don't need to have a personnel time putting all the screws. Another example of how we are combining simulation with AM is a 1-to-8 horn array antenna that I was also passing before. And this is done in collaboration with Ericsson that we're working now. This is in Ka-band, so around 20-30 GHz. That's something regarding 5G. And in this case, we were doing 1-to-8 horn array antenna. So we have one single input and we have 8 horn outputs. So the simulation comes here, and basically you have your input, and then the power is spread toward the 8 different horn antennas that you have in the aperture. You might ask why using 8 and not 1, because you are having more directivity, so you are pointing exactly your customer. You are not spreading the power towards a lot of different directions, and this is where the future of the communication devices and systems are trying to go. It's like to point each of the different customer, so you are not spreading power and you are more efficient. Regarding the process a little bit, so we did everything, as I was explaining before, with CST and SolidWorks from the Sol systems. We started from the vacuum model that I was explaining before, then we jumped to create this mechanical model, which basically is a lightweight component, is conformal to the shape as I was explaining before, and then we were adding the flange to connect with the actual system. After that, since we have the capability and we have the freedom of additive manufacturing, we were adding this honeycomb structure to improve the mechanical properties, because this is something that you can do thanks to this freedom. You're not constrained to have a big block which is completely solid. And then finally, after designing and validating everything, we tested by manufacturing the component that I was showing before with a really low surface roughness, which is also the value proposition of the company. We are reducing the roughness in the AM components compared to our competitors. In order to finalize the presentation, I would like to conclude first by saying that innovation is a combination, and it's driven by a combination of new technologies with simulation tools. Even though we are a hardware company, because we are producing things, we cannot live without simulation. We need to test everything before, and we need to design in some kind of digital platform. We also believe that AEM, additive manufacturing, is going to be the future for many sectors, but specifically for the microwave sector, we are seeing the trend that is going to be the future. We can have robust and monolithic components solving a lot of problems, reducing not only the waste, but also the material and the weight in many systems for aerospace applications. It's a cost-effective solution. We've been reducing the price in client systems by 8 times. And the last thing is that you can create arbitrary shapes. You can create new things that were not even possible before. This geodesic lens that I was showing in the image, if I show this to a senior antenna engineer with more than 40 years in the industry, he's going to tell me this was not possible even done like 10 years ago. So these technologies enable a lot of innovation in the sector. And just to conclude, all simulations and renders that are shown in this presentation are done either in CST, SolidWorks, or Visualize from the Sol systems. Finally, our aim in the company is, as Johan was explaining before, to turn and to realize whatever you have in mind into a manufactured and tested parts. So that is the end of the presentation. If you now have any questions,